guest today. This is RISE Learning Machines Seminars. RISE is Sweden's public research institute. My name is Olof Mogren, and I'm head of deep learning research here and chair of these weekly learning machines seminars, carrying talks from experts in the field from all around the world. We run many exciting applied AI research projects with a wide array of topics with partners in industry, academia, and other actors of society. And the meeting today will be recorded. So if anyone wants to be removed from this recording, just let us know by dropping me an email afterwards. Today, I have the pleasure to introduce Professor Priya Donti from MIT, and who is the co-founder of Climate Change AI, a global non-profit initiative to catalyze the impactful work at the intersection of climate change and machine learning. Priya received her PhD in computer science and public policy from Carnegie Mellon University, and her research interests are within machine learning for forecasting, optimization, and control in high renewable power grids. Priya has received a large number of awards during her relatively short time as a researcher, and will be speaking today about optimization in the loop, machine learning for energy and climate. And with this said, I will stop my screen sharing and hand over the floor to you.
Fantastic. Olof, thank you for the kind introduction, and I'm really excited to be speaking with you all today. Yeah, so I'm going to dive ahead right in and talk about this work on optimization in the loop machine learning for energy and climate. So given the sort of set of people who are here, I almost feel like I don't have to do this upfront motivation, but I'm going to go for it anyway, and sort of note that climate change is one of the most pressing issues that we as a society are facing today, and we're already feeling its effects, from storms to droughts to fires to flooding. These impacts are being felt globally, and they are disproportionately being felt by the world's most disadvantaged populations, which creates an extra imperative to act quickly on this issue. In particular, according to the UN Intergovernmental Panel on Climate Change, we as a society need to hit net zero greenhouse gas emissions by 2050 in order to avoid some of the worst impacts of climate change. And this requires a rapid transformation across virtually every sector of society, from energy to transport to agriculture to industry and so forth. And so my background is in machine learning, and sort of in recognition that kind of making this this huge societal transformation will require us to employ all of the tools and skill sets we have at our disposal, it then became natural to ask, are there ways that tools from AI and machine learning can play a role in helping us to address climate change related problems? And several years ago, a group of collaborators and I wrote this paper called Tackling Climate Change with Machine Learning. We spent, several months kind of surveying the literature, talking to people working in the area to really try to understand where are the actual places that machine learning can add value in climate change related problems. And we found a wide variety of applications here, from helping to better forecast solar and wind on electric power grids in order to enable their integration into those grids, to optimizing heating and cooling systems in buildings to improve their efficiency, to predicting the carbon content of soil in order to then allow us to shape agricultural practices to better sequester that carbon in the soil. And if I understand correctly, I think there's several other authors of this paper who are speaking as part of this webinar series, and so hopefully you'll enjoy hearing from them as well. But when we kind of put this paper together, there are lots of places that AI and machine learning techniques that already exist today can be employed in climate action, but also several applications where we saw fundamental limitations of existing machine learning tools that could be surmounted by additional research in order to enable their applicability to climate change related challenges. And so today I want to focus in on one of these potential limitations of machine learning methods and kind of my attempts to address some of them. And so my work has specifically focused on machine learning in the electric power sector. And as motivation for the kind of direction of machine learning innovation that I'll talk about here, I want to motivate that basically power problems and many energy problems involve physics, hard constraints, and decision-making processes that need to be respected whenever doing kind of any kind of optimization or control action on the system. So electric power grids contribute about 1/4 of global greenhouse gas emissions, and the efforts to decarbonize them involve integrating a combination of time-varying renewables as well as other low-carbon energy sources. But making these kinds of large-scale changes to the grid can be challenging because these power grids are governed by physics and hard constraints. So really quickly, when I talk about power grids, I'm talking about the systems through which our electricity is produced, is then transported along lines and electrical equipment, and is then consumed by end-use consumers like us. These systems are fundamentally governed by various sorts of physics. So for example, if we put power into a power grid, that power is going to flow along the lines and through the electrical equipment in a way that is dictated by the physics of the underlying system. We also have various hard engineering constraints that occur on the system. Things like, if I have a power generator that is producing a certain amount of power right now, I can only change its power output from one moment to the next by a certain amount because of just the physical characteristics of the underlying equipment. And similarly, it takes time to turn power generators on or off. In addition to that, we have various stability constraints that we're needing to maintain on the power grid to make sure that the grid is staying near some sort of electrical equilibrium. And then layered on top of that, we have all sorts of decision-making processes. For example, given some uncertain electricity demand, how do we schedule supply to minimize costs or optimize for reliability given all of these constraints? Now, as we start to, these physics and hard constraints and decision-making procedures have been traditionally dealt with through classical optimization and control techniques, where you're actually able to write down all of these considerations mathematically and explicitly solve for an optimization decision or a controller that satisfies these physics and hard constraints. But what we're starting to see is, as we start to decarbonize power grids, because of the way in which we're doing this, we're needing to solve power grid problems at greater speed and greater scale. Because we're, for example, introducing renewables whose output varies from moment to moment based on the weather. We're introducing a larger number of distributed devices like batteries, like electric vehicles that we're hooking up to the grid. And so this really blows up the scale of the problem that we're trying to solve and the speed at which we need to solve it. And the classical optimization and control techniques are really struggling to cope with this speed and scale. So this has caused kind of a question of, okay, well, if classical optimization and control is struggling here, is machine learning a better alternative? Because machine learning can ingest data and use that to make very quickly output some kind of decision as to what action should be taken on a power grid. But coming back to this issue of, are machine learning methods out of the box suited to do this? While they can satisfy this, idea of needing speed and scale, machine learning methods do struggle to enforce physics and hard constraints and decision-making procedures in a way that is problematic on power grids. If you don't satisfy your hard constraints, you might black out the power grid, leading to large-scale outages, loss of lives, something we really can't afford. And so one might hope, are there ways that we can construct machine learning methods that are able to satisfy these physics and hard constraints? And so that's what I'm going to talk about throughout this talk. And to motivate this, I'm going to give two examples that'll kind of guide our exploration here. So one place machine learning has been proposed to be used is to help us adaptively control different components on the power grid, so power generators and inverters and batteries. And the benefit machine learning brings is that it can really provide dynamic and data-driven control strategies, really see what's happening in the underlying sensors, figure out the patterns, and figure out what action to take based on that. The limitation is that machine learning, in doing that, is optimizing for average case performance. It wants to do as well as possible most of the time. But in doing so, it might sacrifice kind of certain robustness guarantees and not enforce various constraints like physics and equipment constraints that we need to satisfy. So when using machine learning, we somehow have to mitigate this limitation. Another place machine learning is actually already very widely used in power grids is in predicting electricity demand. machine learning has really shown a lot of strength in time series forecasting, in being able to integrate many different modalities and sources of data. And so it is already kind of implemented in many control rooms for this purpose. But the limitation and challenge here is that machine learning methods are often kind of constructed and trained separately without consideration of the broader process that actually uses them. So when I create a machine learning based forecast of electricity demand, my first thought would be, okay, I'm going to try to create a forecast that's as accurate as possible. I'm going to go over here, construct some accuracy optimizing forecast for electricity demand. I'm going to package that up, send that to the power system operator. And if you get a perfect forecast, that's great, but our forecasts are never perfect. And accuracy doesn't necessarily capture, in all cases, the quality of the decision or the trade-offs really in terms of what kind of forecast is good or bad for the decision maker. In particular, if I under forecast electricity demand or I over forecast electricity demand, from an accuracy perspective, an under forecast and over forecast might look very similar, but they have very different implications for how power is actually scheduled. So machine learning methods today are not taking into account these downstream decision-making processes. And this is something that we also need to account for. And so my work again looks at this idea of how do we reap the benefits of the machine learning methods while mitigating their limitations. In order to do this, my work proposes a framework called optimization in the loop machine learning. And this is a framework for developing machine learning methods that incorporate knowledge of these physics or hard constraints or downstream decision-making procedures through the use of optimization problems. Now, for those who are familiar with machine learning, if you hear the words machine learning and optimization, you might ask, are you talking about the way in which machine learning methods are optimized? Or are you talking about things like gradient descent and deep learning? And I'm actually not talking about that in this case. What I mean by optimization in the loop machine learning is that we can formulate optimization problems that explicitly capture the physics or hard constraints or decision-making procedures that we care about, and then embed them into our machine learning model or into the objective function that the model is using to learn, in order to ensure that inherently the machine learning method is capturing the physics and constraints that we care about. So to kind of come back to these two examples that I motivated earlier, I want to kind of show at a high level what this could mean, and then I'll, in the rest of this talk, really try to instantiate that in more detail. So in doing that, I'm going to use this high level representation of a machine learning model, where X are the inputs to the model, H is the functional form of the model, theta are the parameters that we can adjust to change the performance of the model, and then H sub theta of X is then my notation for the outputs. So earlier on, I motivated first this idea of, machine learning being used for adaptive control of different power grid components. And this is a setting where you might think of like a reinforcement learning style machine learning algorithm, where your model is taking in some knowledge of the state of your underlying system, and it's outputting some kind of control action. In general, this control action wouldn't necessarily have any safety or robustness guarantees associated with it. And so the question is, can we somehow write down those safety and robustness guarantees as an optimization problem that we can embed within the machine learning model to ensure that the action the model is outputting is going to be safe? So this is one way that optimization in the loop machine learning could play out. The other example I gave before is prediction, trying to predict electricity demand on power grids. And this would be a time series forecasting kind of setting, where you have, your model has input historical data, and it outputs some kind of demand prediction. But as I mentioned before, that demand prediction doesn't live in a vacuum. That prediction is going to be used to make some kind of decision downstream about how to schedule power. And so we can write down the relationship between our prediction and the downstream decision-making process as an optimization problem. Then one might hope there's a way to then feed back information about the downstream decision-making process to our forecasting model, so that our model can avoid making prediction mistakes that are particularly bad for the decision maker. So this is another way optimization in the loop machine learning could play out. And so in the rest of this talk, having motivated hopefully what optimization in the loop machine learning is and why we might need it, I want to dive further into the details of these applications. So first, I want to talk about how does this actually work? So far, I've drawn some boxes inside other boxes on a slide, but you probably want to understand, what does differentiable optimization or optimization in the loop machine learning actually look like? So I'm going to talk about that. And then I'll dive into the two settings that I talked about earlier. One of them is enforcing hard constraints in reinforcement learning settings, and the other is creating time series forecasting models that are cognizant of their downstream decision-making processes. So Olaf, I want to ask, is this, in the seminar, I'm happy to open up to questions as I go or wait till the end, however you'd like.
It's up to you.
Okay, so I'm going to pause. If anybody has any questions now, I'm happy to take them.
Yeah, I have a question actually. My name is Leif Jonsson. I'm at Ericsson. I was just wondering, and maybe you'll get to that already, but when you say optimization here, do you mean provably optimal solutions, or is it just optimization in general?
It's a great question. So I'll sort of let me defer the answer to that question. It's a really good one, and I'll get to that in just a moment. So thank you. Any other questions? Okay, so I'm going to dive in and get to your questions sooner rather than later. So, right. So far I've talked about this idea of, embedding optimization problems somehow into machine learning methods, but how am I actually doing that? And the approach that we take in our work is to embed optimization problems as layers within deep neural networks. And so I'll talk first about a general framework that we developed for this, and then also highlight additional tools that now exist in the ecosystem to allow you to do this in a much more exhaustive way at this point. So to give some background on deep learning for those who may not be familiar, you might kind of recognize this, pictorial depiction of a machine learning model from before, where again, X are the inputs, H is the functional form of our model, theta are the model parameters, and H sub theta of X are the outputs. I also want to introduce one additional concept here called the loss function. And this is the function that basically gives some kind of score for the quality of the output of the machine learning model. And upon computing that score, the model is then updated using feedback about that score in order to try to improve the score. And by convention, lower values are better here. So when we talk about deep learning, what we're basically saying is we're going to choose a functional form for our machine learning model, and that functional form is given by a neural network. A neural network is just a bunch of functions composed together, and these functions are generally nonlinear, and they have parameters that we can adjust in order to change the performance of the model. And each of these functions that are composed together, we call them layers. And the way the parameters of these layers are updated is via a process called backpropagation and gradient descent. Basically, we put some information inputs into our neural network model. It produces some kind of output. We compute using the loss function how good that output is. And then we compute the gradient or derivative of the loss function with respect to all of our parameters. And we use that information to update all of the parameters accordingly. And because this is how neural networks are trained, using this process of backpropagation and gradient descent, the consequence is that every single component of our kind of deep learning model, so that's every single layer within the neural network, as well as our loss function, has to be differentiable. I need to be able to take derivatives through it. And so if I'm telling you that we're somehow embedding optimization problems into our neural network as layers are in our loss function, then I need to be able to motivate to you, how do we actually make these differentiable? And so the key insight here is that what we do is that after solving an optimization problem and getting its solution, we're able to write down certain optimality conditions that those solutions satisfy. and figure out a way to actually take derivatives through those optimality conditions. So I'm going to give an example here. Imagine that you want to embed this optimization problem, which is a convex quadratic program, into your neural network as a layer. To Leif's question, we are actually writing down this optimization problem and we are actually solving it using a traditional solver. So there isn't any sort of, approximation here where you're actually getting to the optimal solution of this optimization problem. Once we have that solution to the optimization problem, then we are able to, in this case, because this optimization problem is convex, we have something called the KKT optimality conditions, which for this problem are necessary and sufficient to describe all optimal solutions of the problem. So basically, given an optimal solution, we know that it satisfies those constraints there on the right. And then what we can do is basically say, great, we have a set of equations that our solution satisfies. We can just take derivatives through that set of equations. And once you do that, you get some matrix that looks something like this, where the middle term here are the gradients that we're trying to compute. These are the gradients of our solutions to the optimization problem, both the primal and dual variables for those who know optimization well. It's the gradient of the solution of the optimization problem with respect to all parameters of the problem. So sort of anything in this problem that I should have actually motivated earlier. In this optimization problem, we're letting Z be the output of the optimization problem, the decision variable, and everything else in here, Q, A, B, G, H, you can view it as either a parameter of the problem that is fixed or something you're feeding in as input that varies. So this middle term here is then the gradients of your optimization problem outputs with respect to all inputs and parameters. And then we have these other terms, the generalized Jacobian of the KKT conditions and the gradients of the problem parameters. So basically a kind of ugly set of equations, but one that we can actually explicitly solve to get the derivative of the output of our optimization problem with respect to all problem inputs and parameters. Now, for those who are really familiar with backpropagation and gradient descent in neural networks, you'll come back to me and say, well, Priya, we never actually want to compute the gradient of the output of the optimization problem with respect to its parameters directly. This is very space inefficient to compute and keep around. We instead want to directly compute the gradient of the loss function with respect to all of our inputs and parameters. And so we kind of do some algebra, go one further step, and use something called the Jacobian vector trick to actually do that. Now, I know I got into some details there, into the weeds. So just zooming out a bit for those who may not have followed all the details, the basic idea here is that we have an optimization problem. We actually write it down, we actually solve it. And then given the solution, we have a way to use some property of the optimization problem. In this case, it's KKT optimality conditions, to figure out what the gradient of that optimization problem output is with respect to all of the inputs and parameters. And this is what allows us to then embed this optimization problem into our neural network. So I'm going to pause there. Leif, in particular, did that sort of answer your question or anything else that you wanted me to clarify there?
Yeah, I'll admit that my theoreticals on Kunkarush-Tucker is rusty, but this still just apply. Well, I shouldn't say just perhaps, but this applies to convex problems, right?
Yes.
Well, we have a lot of problems that are not necessarily convex, so we don't know if they're convex or not. So
that's right.
And here we're talking about gradients, so we're talking about some kind of gradient descent. And I guess are we guaranteed to reach a global minimum or maximum or whatever you see?
That's a great question. So I'll get to one of those questions in this slide, and then I'll get back to the other question as well. So the kind of framework I showed was illustrative to talk about like how do we actually do this differentiation through convex optimization problems using KKT conditions. Since then, there have been others who have used similar kinds of techniques or similar kinds of thinking to propose ways to differentiate through other types of problems as well, including non-convex ones. So combinatorial optimization problems, non-convex power grid optimization problems, maximum satisfiability problems, and many other sorts of problems. in some cases using, right, like KKT optimality in the cases where you can do that because of convexity, but in other cases, for example, trying to find other fixed point equations that a solution might satisfy and differentiating through those. Now, in terms of kind of the, are you guaranteed a global optimum? So again, for the actual solving of the optimization problem, we are using sort of a traditional optimization solver. So we kind of inherit all of the, benefits and limitations of those solvers. So if you have, for example, a convex optimization problem where you have a solver, a traditional optimization solver, you generally are guaranteed to get to a global optimum. If you have a non-convex problem, you're not necessarily guaranteed to get to a global optimum of solving that problem. So we inherit all of the benefits and limitations of that solver. But the key idea is that fundamentally what we're doing is that all of the slides I just talked about are talking about this one specific module in the neural network. So how you get from input to output is by solving the optimization problem using a traditional solver. How you get from output to input gradient is by differentiating through some property at the solution of the optimization problem. And this module lives within this broader neural network where there's some backpropagation and gradient descent going on, and where that does not necessarily have global optimality guarantees. But it's almost like this little layer in the middle. We are solving the problem as best we can using a traditional solver. We're getting a gradient that allows us to differentiate through this. And that is then just a module within a broader neural network that is optimized in the way that neural networks are.
Question?
Yes.
What kind of, in the kind of applications that you're using this, what kind of computational overhead does this incur?
It's a great question. So the kind of cost of running an optimization layer is much higher than running kind of a standard layer. And so you're often making some trade-offs about, for example, can you come up with a way to, if you need really fast inference at test time, then is there a way to kind of make the optimization part only be there during training, where maybe you have a little more of a time budget and then inference is still fast because you've sort of abstracted the optimization part to, say, a loss function that would only be used during training. There are other cases where you maybe are looking at a situation where if you had to learn your optimization constraints from scratch, you would have to use a lot more data. Whereas if you're able to like provide some priors to your model, then the thing becomes much more data efficient. So there can be these trade-offs in terms of you're spending a little more compute budget every time you run the model, but you're not needing to run it as much, or like it takes much less time to train from a kind of number of iterations or amount of data perspective. So there's some trade-offs we're often looking at there.
Right.
Yeah.
We have a question from Tepide as well.
Yes.
I don't know if this is a stupid question or it's an obvious one, but so you place this optimization layer somewhere within the deep neural network, but the construction of it was heavily dependent on the input. So does it mean that we have to always place it in the beginning of the network, or can we really place it anywhere in the network? And then does the meaning changes by doing that?
That's a really fantastic question. So you're absolutely right. Sort of the meaning of the inputs matters. And there's two ways to think about this. In cases where it's an optimization problem that you really care about, you know that there is some meaning to the inputs, placing it as the first layer can make sense. Placing it as the last layer makes sense in the case where you need the outputs to have a certain meaning. And when you place it in the middle of a neural network, you can do things like pre-train the part of the neural network that is feeding into the optimization layer. So you know the outputs are in some kind of reasonable regime to be inputs. And then you stick the rest of the network on and continue training the whole thing end to end. So in a case where you have an optimization problem where you really you care about that optimization problem, you care about the meanings of the inputs and outputs, you do have to do some things to make sure that the inputs and outputs make sense. You can also think of an optimization layer though, like a generic building block. You might throw in a convolutional layer, you might throw in an optimization layer with some learnable parameters in it. And in that situation, you can just sort of throw it in the sense that if it's not that you're solving a specific optimization problem, but you just have some prior that optimization is a good prior to embed into my neural network, then you can kind of treat it like any other building block. Yeah, that's a great question. Awesome. Amal.
Yeah, hi. Well, my question is basically, in this layer of optimization, can we sort of also use some random variables? Like if we assume some uncertainty on the production and consumption, and we want to solve it as a robust model,
Yes.
under some uncertainty set, is that also possible?
It is. So yeah, you can, for example, like write down some kind of stochastic optimization problem. Now you have to think then about like, how do I differentiate through this? Am I going to differentiate through this at, like, am I going to pretend it's deterministic when differentiation? Do I have some expectation that I can write in like closed form? I gloss over the details of that in this talk, but in the second example I'll give, we actually do something like that. So the answer is yes, you can kind of do robust optimization and stochastic optimization, but you will need to sort of think about the details of your problem structure to figure out how exactly to make it differentiable or what assumptions you're willing to make in order to make it differentiable.
Thank you.
Yeah. Awesome. Well, thanks for the great questions there. Yeah. And so basically the point of this portion of the talk is to basically say that at this point, optimization can really be viewed as a primitive, as a type of layer within neural networks, in the same way we think about embedding like a sigmoid layer or a ReLU layer or a convolutional layer, which comes with its own benefits and trade-offs, but fundamentally something that we have in our toolkit. And so the question is, now that we have this toolkit, how can we actually use it? And that's what I want to get into in the rest of the talk, kind of coming back to these two examples I motivated earlier in the context of power grids to give examples of how optimization in the loop machine learning can play out. All right. So as I motivated a bit earlier, on power grids, we are starting to need, control methods that can perform well so that it can really deal with the scale of the power grid, the sort of non-linearities, the data-driven dynamics, all of those kinds of things, but that also guarantee enforcement of hard constraints. And the approach we take is to construct machine learning methods using this optimization in the loop paradigm, so optimization in the loop reinforcement learning, in a way that aims to actually guarantee enforcement of hard constraints. So I'll dive most deeply into a particular setting, enforcing asymptotic stability in power grids, but then I'll briefly zoom out to just motivate that even though I dive into the details of that specific setting, that this broader paradigm is applicable across a wide range of physical settings as well. So when it comes to thinking about the control of systems, there are actually two communities that are working on this in parallel and take relatively different perspectives on this issue. So the first is the reinforcement learning community, and recently the deep reinforcement learning community, which basically say, given some simulator of our underlying system, we're going to throw a machine learning algorithm at it that is going to propose some kind of policy for taking actions on the system, get feedback in the form of a reward as to how good or bad that proposed actions are, and then iteratively update over time by doing just more and more iterations in the simulator to try to get a control policy that is getting a good reward. So basically trial and error. And the pro here is that you get really expressive and well-performing policies that are really able to glean like the nuances of what's going on in the underlying system and come up with policies that are really tightly crafted to act based on the patterns in that underlying data. For example, we've seen a lot of breakthroughs in deep reinforcement learning in settings like, multiplayer online games like Dota 2, just completely beating human players. Now, the reason we've seen those successes in places like Dota 2 is because those are places where you can afford to say, okay, my goal is to, on average, win significantly. And if I lose once or twice, that's not a big deal. On average, I'm winning. But you can, in these settings, have failures and potentially catastrophic failures, because there are no kind of guarantees on the performance of the method. And this is a non-starter in places like power grids, where again, catastrophic failures are indeed actually catastrophic. So on the other side of this issue, you have the control theory community, and within that, the robust control community. And what this community says is, we're going to write down some uncertainty set in which our underlying dynamics lie. And we're going to write down some guarantee on the stability or robustness of our controller that needs to be satisfied. And we're going to explicitly solve an optimization problem to spit out a controller with provable stability guarantees, as well as some kind of certificate like a Lyapunov function that is in fact showing that that guarantee is being satisfied. And the pro here is that you have a controller that you can actually reason about its behavior. You have some kind of provable stability guarantee, which on a system like a power grid is really important. The challenge, though, is in going through this procedure of writing down your uncertainty set for the dynamics, writing down your controller, writing down the stability guarantee, you often tend to make a lot of assumptions on and limitations on the functional form of your controller and your system. For example, that your controller is linear in order to actually get an optimization problem you can solve. And so the result is that you get overly simple, sometimes overly conservative control policies, for example, linear policies, that are not kind of appropriately performing and or able to really deal with the fact that the underlying system is nonlinear and has sort of additional ways that the controller can be improved. And so what our work looks at is trying to think about, well, can we somehow mix between these two worlds? Can we improve performance in the same trial and error way that deep reinforcement learning does, and actually learn from the underlying data while still guaranteeing stability in the same way that robust control does? And in some sense, the idea here is relatively simple. What we do is we start with a neural network that takes in information about the state of the underlying system and proposes some kind of control action. This isn't the action we end up taking, however. What we end up doing is we end up projecting this action onto a set of actions that we've derived as being safe. And then we take the action that is actually the output of that projection. This is then our model. It's a neural network with a neural network followed by a projection onto a set of safe actions. And a projection can be implemented as an optimization problem. And as I've motivated, we have ways now to differentiate through optimization problems to basically treat this projection just like any other neural network layer. And so we train this model in basically the same way we would train any other kind of reinforcement learning model. We get some notion of reward, we get some notion of gradients, and we update the neural network accordingly. The result is that you have now a deep learning-based policy that has provable robustness guarantees because of this projection, because this projection layer is enforcing some property about the action that is being output. And this is true, by the way, even if you have a randomly initialized neural network. So the first part of this is really terrible. You are still enforcing some property on the output of your neural network. So even right at the start, you have some provable robustness guarantee on your output action. But you're able to train this neural network using standard reinforcement learning approaches by trial and error in order to then improve its performance accordingly. Leif.
Yeah, perhaps I missed it, but it seems to me that this projection, isn't that a discrete thing? Can you do that by differentiation backwards?
Yeah, it's a good question. So I'll get into the details of this on the next slide, but this projection ends up being a L2 projection onto a second order cone, which is a continuous optimization problem. And in this case happens to be convex. And so we can then use the kind of same kinds of techniques I talked about earlier in implicit differentiation. Awesome. And yeah, and I'm going to go through these details fairly quickly because I know they may not be of ultimately huge interest to everybody in this audience, but just to give a sense of what's going on here. I really glossed over in this last slide the fact that we need to somehow magically find the set of actions that we're projecting onto that are magically giving us some kind of stability guarantees. And the way we do that is honestly just reusing a bunch of existing machinery from control theory in order to find a set of actions that are guaranteed to satisfy what are called Lyapunov stability criteria at our given state, even under kind of worst case instantiations of uncertainty in our underlying system. So from control theory, we basically take a couple of things. So one is we have an uncertainty model of our underlying dynamics. Here, X is the state, U is the action we're taking, and W is some uncontrollable disturbance. And this is sort of an example of what an uncertainty model might look like. It's a setting where we don't fully know the underlying dynamics, but we are able to somehow characterize our uncertainty and how those dynamics might play out. This kind of model, for those who know control, it's called a linear model in the sense that our time evolution of the state is characterized by a linear function of our state, our action, and our disturbance. But the dynamics that our linear model describes can actually be highly nonlinear because this uncontrollable disturbance can in theory be a highly nonlinear function of our state or our action of various exogenous factors. And we have some bound on our disturbance, but we don't know exactly what it looks like. So linear system, quote unquote, terminology wise, but this actually can describe really highly nonlinear dynamics. We also have something called the Lyapunov function, which we obtain using robust control. And a Lyapunov function can be thought of as a potential function for your system. It's a non-negative function where higher values are indicative that you're farther away from stability, and values closer to zero are indicating that you're closer to some kind of stability or equilibrium. And so reflecting that, we have some kind of criterion that we impose on our Lyapunov function called the exponential stability criterion, which basically says, if you're able to produce a controller that is reducing the value of your Lyapunov function by at least a certain amount at every point in time, then that means that you're driving your Lyapunov function to zero. So you're driving it towards stability. And then you're able to basically show, if I drive my Lyapunov function to zero, then I have a provably stabilizing controller. And so what we do is we basically say, imagine that I am at a specific state in my system right now. And I have a Lyapunov function that I've obtained using traditional robust control techniques. Let me actually analytically figure out what is the set of actions that satisfy my exponential stability criterion, even when my dynamics, so the uncertainty in my dynamics, play out as badly as possible. And that looks something like this. Basically, we have this exponential stability criterion. The left side is the one that depends on the uncertainty in the dynamics. So we basically say, this is an inequality. So if the left side is as big as possible, we still want it to be less than or equal to the right side. And we want to pick an action that will cause that to be true. And you can basically just do some algebra to figure out what is the set of actions that will guarantee that my left side is less than or equal to my right side, even if the uncertainty is as bad as possible. And in this case, this ends up looking like this. So this sort of second order cone set, which is a convex set. And we also, because of the details of how we obtained our Lyapunov function, happen to know that it's non-empty as well. And so we can then frame the L2 projection of the action output by our neural network onto this set as a convex optimization problem, which we can then embed as a layer in our neural network and differentiate through in the way that I mentioned on the previous slide. So why go through all the trouble here, right? And so I'm going to kind of show some results on a synthetic norm-bounded linear differential inclusion system, the type of system I talked about on the previous slide to illustrate this. So on this slide, we're seeing the performance of a couple of different kinds of methods compared against each other. The first set are non-robust methods coming from both control theory and reinforcement learning. In the middle here, we have a robust control method. And in the paper, we compare against more, but just only so much space on the slide. And then the last two columns here are two different variants of our methods. So same underlying neural network architecture, just trained using two different types of reinforcement learning algorithms. And these are being compared against each other on the basis of a notion of control cost called LQR cost, where lower values are better. And I'll note that this is on a log scale. And we compare these methods in two different settings. One of them is an ordinary setting, where during training, the model is seeing some kind of uncertainty in the system, some distribution of uncertainty in the system. And during testing, it's seeing a pretty similar distribution of uncertainty. And we also look at an adversarial setting where the model is again trained on a system as usual, but when it's tested, we construct an adversarial worst case disturbance or worst case uncertainty tuned for every single model individually to basically figure out like what is the worst this model could do. If we got the kind of the worst instantiation of uncertainty thrown at it, what would happen? And so there are a couple of things to notice here. So when we compare our methods against a robust control method in the ordinary case, we improve in ordinary case performance compared to a robust control method. And in some sense, this makes sense. The robust control method has a much more limited functional form. It's very conservative. Our method is able to actually look at the system, learn from the underlying data how to improve the control policy to improve average case performance. Now, our methods are not as good in some cases as non-robust methods. For example, you can see a few methods here that are improving by orders of magnitude compared to our methods in average case performance. But when you look at those same non-robust methods in the adversarial case, they all blow up. They all go fully unstable, whereas all of the robust methods, including ours, stay stable. And so this is the key kind of, benefit and trade-off that we're trying to hit here, that we want methods that are not so overly conservative that they're missing opportunities to perform well when the system is operating as usual. But we still want to make sure that if something adversarial or bad happens and the system blows up, that we can really say something about how these methods will perform, that they will probably not destabilize the system. Now, coming back to a question that is asked before, often there is no free lunch. And so the downside here is right now that our methods are, of all the methods that are on this slide, kind of the most computationally intensive, and sort of bringing down those computational costs by either solving kind of reduced form versions of the optimization problem or figuring out, do I only need to solve the optimization problem every now and then? Can I circumvent it every now and then because I can somehow incentivize my policy to be stabilizing the system? There's, I think, a lot of work to be done there. But yeah, at this point, the trade-off of improved average case performance, stability under worst case dynamics is sort of what we're trying to hit with these new methods. So I did kind of get into the weeds of this specific setting of asymptotic stability in power grids and all the math behind that. And so I just want to zoom out and note that this paradigm of, have a machine learning, a neural network-based reinforcement learning controller whose output is constrained in a differentiable way extends beyond just this one setting. So we kind of employ very similar thinking to construct a controller for optimizing the heating and cooling system in a building, where the goal is to minimize energy use, but the constraints we need to respect include equipment constraints on the supply water temperature giving to the heating and cooling system. And we also need to maintain constraints on thermal comfort, making sure the building stays within certain temperature ranges in the output. And the kind of methodology is relatively similar. We again have a neural network with a projection onto a set of feasible actions. And this is the neural network we train. And where the details that really are important is how do you actually construct this projection onto a set of feasible actions using domain knowledge, and how do you actually differentiate through that? So to summarize this part of the talk, the idea is that we really want these well-performing control methods that can really, look at the data in the underlying system to get better performance, but that also guarantee enforcement of hard constraints. And the basic idea here is that we can project the outputs of a neural network onto a set of safe actions that we obtain using domain knowledge. And if we can make this projection differentiable, then we can train this whole model end to end in the same way you would train a reinforcement learning algorithm. And there's some additional, fun future directions here, including, additional paradigms for bridging reinforcement learning and robust control, as well as improving computational costs. So in the interest of time, I am going to dive into this last section, but try to keep it to just a couple of minutes so we have a little bit of time for additional questions at the end. But I motivated at the beginning that an additional setting that we care about using optimization in the loop machine learning in is forecasting. So again, the motivation here is that we are often using machine learning to do some kind of predictive method, but these predictive methods operate within some larger decision-making process. And not all mistakes are created equal when it comes to the output of the machine learning model. We somehow want to take that into account. And so our approach is to construct these decision cognizant forecasting models using this paradigm of optimization in the loop learning. And as I motivated before, we look at this in the context of electricity demand forecasting, but we also look at it in some other settings. So the setting we're looking at here is one where we want to predict electricity demand in the future over the next, like we're at the beginning of a day, hourly for the next 24 hours, based on some past information. Usually what we would do is try to minimize some kind of distance between our predicted electricity demand and our actual electricity demand. And to, I think it was Amal's question earlier, you could do this in a deterministic setting where here your loss function is something like root mean squared error. You could do this in a probabilistic setting where you're maybe trying to minimize like negative log likelihood or something like this. But usually you're just trying to minimize some distance between your predicted quantities and your actual quantities in order to improve accuracy. But as I described earlier, when we make a prediction, someone is going to make a decision based on that. So in this case, if we make an electricity demand prediction, a power system operator will schedule electricity generation on top of that. And one might argue that what we actually care about is how good was the decision made by the power system operator when it then actually acted on our real system. So this is what the new loss function that we optimize for. We ask the question of, if I put historical information into a neural network with parameters theta, it's going to create some kind of prediction of future electricity demand. That prediction is going to be used to make some kind of decision of how to schedule electricity generation. And we'll call Z star the kind of best decision that could be made on the basis of our prediction. What we then care about is how good was the decision when it acts upon the true electricity demand in the future. So I made a decision based on a prediction. That decision is going to act on the true system in the future. How good is that decision? And so this is the loss function that we now optimize for. The quality of the decision that is implied by our prediction is now what we're measuring. And so this is what our decision cognizant model looks like. We have a neural network that is taking in some past information and predicting electricity demand. We then put that electricity demand into a power system optimization model, solve for what the power generation schedule would be, and then assess the cost of that power generation schedule against the true electricity demand. And since the optimization problem is differentiable, we're able to backpropagate through it. Again, back to Amal's question here, in our setting, I'm going to gloss over this, but we actually look at doing a probabilistic prediction, and we have to make some assumptions like we assume that this predicted demand is going to be Gaussian distributed. So we actually just predict the mean and standard deviation of the Gaussian distribution. We're then able to, for our power system optimization model, write down in closed form what the expectations would look like as a function of our distribution parameters, and then we're able to differentiate through that version of the problem. There are other ways to do this, but basically to say there is a way to sort of get some kind of like probabilistic prediction and stochastic optimization within this framework. But zooming back, basically the idea is make a prediction, figure out what the decision is implied by that prediction, see how good that decision is. And this kind of decision cognizant approach can really dramatically improve outcomes when it comes to the generation scheduling problem. So the basically quality of the downstream decision-making process. And to demonstrate this, I want to show two plots. Both of these plots are comparing our kind of decision cognizant method, the green solid line, against a method that is just trying to optimize for the accuracy of the forecast. This is the red dashed line. On the left plot, these two models are compared on the basis of accuracy. And maybe unsurprisingly, the accuracy optimizing model does better than our decision cognizant model. That's what it's optimizing for. But when we look at those same two models on the basis of what was the quality of the decision downstream, so we have a decision cost in the right plot where lower values are better, you can see the cost of the decision, so the negative consequences of the decision were far less in the case of the task-based model rather than the kind of accuracy optimizing model. And in fact, taking this decision cognizant approach can give an almost 40% improvement in the cost of the decision-making process, but basically just avoiding predictions that are particularly bad from the perspective of the decision maker. So just to wrap up super quickly here, we use the same kind of thinking to do things like approximating power system optimization problems where your downstream decision-making process refers to the physics of your system. And generally this idea comes into play where when you have a model that its prediction is going to interact downstream with some kind of decision-making process, with some kinds of physics, something else that you think the model should take into account to avoid making mistakes that are particularly bad, then what you can do is incorporate knowledge of that downstream decision-making or physics into the loss function via differentiable optimization. And I think, again, there's some really interesting directions here in incorporating a wider range of decision-making paradigms and understanding trade-offs between task-agnostic and task-based models. So to summarize, today I talked about optimization in the loop machine learning, so a framework for embedding physics hard constraints into machine learning models using optimization problems, and talked about two different ways that this can play out in reinforcement learning and downstream decision-making. And last but not least, I want to mention, if you are interested in this broader, community, this work is motivated by, again, leveraging machine learning to address climate change related problems. If you're interested in this broader area of work, I would encourage you to check out the Climate Change AI community, a place to find resources, people, funding, and other kind of opportunities to really disseminate your work, meet others, and hopefully, work forward more effectively on using machine learning for climate change related challenges. So with that, thank you so much for all the great questions and discussions so far. And I am looking forward to taking any additional questions we might have time for.
Thank you, Priya.
Thank you.
We have a raised hand from Amal.
Yes.
Yeah, I was wondering, I think 3 slides before when you talked about the cost of the decision, I was mainly wondering, are you talking here like NMAT hours or actual cost, or like unsatisfaction, or like what's
so here the cost is a combination of like actual economic cost. So how much cost is it, how much is it costing to produce power, as well as a notion of kind of constraint unsatisfaction. So like a reliability cost or a stability cost.
Mm-hmm. Okay, thank you.
Would you say do you have some reflection on the generality of modeling things like this?
Yeah. It's a great question. And honestly, no, I think this is something that is like a really interesting line of work to think about where, so details wise, what we end up doing is we actually end up training our model using first accuracy to get it into a like base representation that looks good. And then we end up fine tuning it based on this task loss. So that's something you can do. But then also the thing that kind of intrigues me is even though we think of as accuracy as our standard metric, there's no reason that's true. I would imagine situations where the accuracy optimizing model would perform better on a different task than this one, than our task-based model, but then another like task number 3, where our task-based model happens to perform better than the accuracy optimizing one. So I think some characterization of, what notions of structural similarity in different tasks cause different representations to work like well across that set of tasks, I think something that's really interesting to explore that we haven't done yet.
Great, thank you.
Awesome.
Leif has another question. And
yeah, that was
let us know if you have to leave.
Sounds good. No, thanks. I think I have time for maybe one more question and then I should hop off. Leif, please.
Yeah, that was certainly very interesting. I mean, a hot topic nowadays are these trustworthiness and explainability aspects. Are there any ways to quantify how far from an optimum are, how kind of explain how we can guarantee these constraints and so on?
Absolutely. Oh, go ahead.
And another addition, how do you see causality related models like causal machine learning fitting into this kind of framework?
That's a great question. So okay, so in terms of like establishing optimality, I think the nice thing about this framework is that in a lot of provable machine learning frameworks, you actually have to prove something about the neural network or machine learning model itself. And this can get really difficult and thorny. In this case, you can actually just prove something about the kind of output of the neural network. So for example, in this robust control work, you don't care what happens in the underlying neural network. I can reason about the output because I know that something about the output is guaranteed by optimization. And so it reduces to just reasoning about optimization the way we're used to, like, is this problem solving to optimality? Is it not? And so forth. And so I think this can be one way, like one pathway to establishing trustworthiness, which is like falling back to the established notions of trustworthiness that we already know how to reason about in other fields, without having to now reason about like the internals of a neural network in a way we don't understand. In terms of causality, I don't necessarily have, stronger informed opinions about that. In this case, there may be way to sort of like embed certain structures that we care about in a causality context into machine learning using this, but I'm certainly not a causality expert. So thanks. All right, I can take this last question from Ehsan.
Okay.
Oh, thank you so much, and thank you for the nice talk. I'm just a bit confused, let's say, about the difference between the network you were talking about using optimization layer at the last layer compared to physics-informed networks that we actually embed some of those equations, like the optimization constraint at the loss function. Mm-hmm. So can you mention the positive effects of using such method?
Yeah. So I think the big difference between embedding something in your network versus embedding something in your loss is whether you are enforcing something or incentivizing something. In your loss function, when you put information about, I have this objective function I want to satisfy, but then I have some other constraints that I'd like to be satisfied, you're in principle giving your model permission to trade off between those things. Whereas when you are enforcing this as a last layer projection, you're not giving your model the option. You're saying enforcement of this, whatever this last layer projection is doing, is a hard constraint. And then on top of that, do as well as you can.
Great. Thank you so much, Priya.
Thank you so
there are
much.
many thank yous in the chat for you appreciating your talk.
Awesome.
We'll be back next week with Natasha Slabdoje of Uppsala University. She'll be talking about multimodal medical imaging. On November 30, we have a speaker from Florida, University of Florida, Ben Weinstein, is going to talk about airborne wildlife detection. So that's sort of the next ecology motivated and climate change motivated talk. So welcome back, and thank you all for today, especially you, Priya.